Goliath finally pushed the damn button. Okay. Okay, yeah, we are live now. Hello everyone. This is something I wanted to do from a long time actually, and the content of this video will be to explore how to apply game hacking, advanced technique for game hacking to PlayStation 2 games. And the game that we are going to test will be Kingdom Hearts 2. And with me, we are four of us, and please guys introduce yourselves.
Hi, I'm Vlad. I go by Vlad ABDF, and I think this is going to be a wonderful learning opportunity for everyone, at least in some way.
And I don't know if the two of you want to introduce yourself, or we can just move on.
I'm someone from the dark. I'm going to be learning with you guys today.
Yeah.
Okay, hi, I'm Riku, and I'm kind of stuck to this game since I don't know how long, and I'm really looking forward to this talk today.
I think that most of us
are all a little too stuck.
Yeah. And I will explain why we are still stuck in this damn game. So, yeah, basically the overview for this video will be to explain why we chosen Kingdom Hearts 2, our guinea pig, for this short talk. A brief overview for PlayStation 2 architecture and MIPS assembly, since MIPS is the architecture that is used for the emotion engine from PS2. RAM hacking with cheat engine, which I guess that almost everyone knows how to use. RAM hacking using EDA Pro or whatever disassembly tool you are going to use. And PCSX2 emulation and its built-in debugger. The requirements. Of course, you need to know how to use a computer, of course. Any operating system, of course I'm using Windows, and because most of the tools I use every day are on Windows, but as I know, you can still do the same thing, even on Linux and macOS. Any memory analysis tool, I will use cheat engine. I don't know any other memory analysis tool. Any disassembler, so EDA3 should work. I'm using EDA Pro for this talk. There is Xeeynamo, which does not have yet a native PlayStation 2 supporting, but as I know there are two GitHub extensions for allowed to load PS2 executables on it, and the most famous PS2 disk, which is kinda old right now, but it does its job. PS2 emulator, and a minimum background of programming knowledge.
Let me interrupt you real quick. Chat saying you're echoing.
Me?
Yeah, it sounds like there are two of you speaking.
Okay, maybe because you have my live open somewhere?
Make sure in OBS that there's only one instance of your microphone as well.
Okay, let me check if I have some technical problems here. What about now?
It sounds fine.
Okay, so no, for you it sounds fine, but it does not sound fine for the one that is following me from YouTube.
Yes. Yeah, it's the chat that thinks you sound echoey.
Okay, thanks Vlad for letting me know, because I was reading PowerPoint, so I was not paying attention to the chat yet. Okay, those are the requirements, and yeah, why I decided to choose Kingdom Hearts 2, because it's one of the most interesting PlayStation 2 games to hack, in my opinion. The main reason is because the game is very data driven, using its in-house engine from Square Enix, where basically even how the enemies or the bosses of the game works are not coded inside the executable, but are coded using some kind of pseudo programming language called AI inside the game files. So basically the executable of the game is just a raw game engine, does not contain any logic. So in theory, as long as we have control of the files, we can do whatever we want. It's fun to play. I think it is one of the best games to play. I think that even the sequel does not compare to Kingdom Hearts 2. There are a lot of modding tools and mods to download, so I think that contributing to explore more about this game will allow in the future to have more mods and more powerful modding tools. And currently we have open source tools and an open source documentation that anyone can download, read, contribute, and do whatever you want. You can fork the entire open source project, and yeah, it's basically open source. And we already have some tools that are being developed by other developers, and I use those tools for this tutorial. So how MIPS processor works for PlayStation 2. So PlayStation 2 has 32 megabyte of main memory. In chat they are saying to me that I'm saying open source. Sorry for the Italian pronunciation anyway, for the Italian accent. So, back on what I was saying, 32 megabyte of main memory. So that's the range of memory that PlayStation 2 uses. In MIPS, every operation code or opcode is 4 bytes long. So, for example, ARM or x86, every opcode, every operation code has a dynamic length. With MIPS, it's 4 bytes long, so everything is aligned and there are no problems on reading that. So it's extremely simple to understand. Almost all PlayStation 2 games are compiled using GCC, using C or C++ code. And this is really important for one slide that I'm going to show you later. And the registers using for MIPS are really easy to understand. So we have between A0 and A3, which are the argument registers. B0 and B1, which are the return values. From T0 to T9 are the temporary registers, and from S0 to S7 are the save registers. So basically, every time that a function inside the game, a PlayStation 2 game, want to perform some kind of operation, they will use from the temporary registers. But when the temporary registers are too much used, the function will sort the temporary register to S0 to S7 to free up some space, basically. We have 3 other registers which are not really are very used by the CPU, but for us it's like not really necessary to understand what they do. And there are PC for program counter, we have the return address and the stack pointer. In the truth, there are other registers, but they are not really useful for this talk, so I'm going to ignore them. So, for now, is everything clear here?
So far, yeah.
Yeah.
Okay. So I will show to you how GCC, the C compiler, converts a function written in C code to MIPS assembly. So we are going to understand how more or less we can read the disassembled code. So we have just a simple function that sums two integer numbers, x and y, and return the result. And below we are calling that function. So as we said before, we have b0, which is the return value register, and we have register from a0 to a3 to represent the arguments. So basically x will become a0 and y will become a1. And after sum will be called, the result of the operation will be stored to v0. Before to call sum, on the MIPS, what MIPS does, it assign 1 to a0, 2 to a1, will call sum, and then at that point we have v0 as with our result. This is a pseudo-compiled code. This is not how the information is represented once you compile that. This is what that pseudo-compiled code will become actually in MIPS assembly. So basically we have a label called sum. We have an operation code called odds. On the right I have the explanation of what that piece of code does. So in this case v0 equal to a0 plus 1. This will return the control to the function that called sum. And here we are going to basically that's the same thing that is on the left. So 1 is stored to a0, 2 is stored to a1. There is a function called JAL, which is jump address location or jump address long, I don't actually remember. And basically it transfers the control from the current execution to the function sum that will process the argument registers, and it will return a v0. I want to...
Real quick. I'm sorry to interrupt. Real quick, what I noticed is when you're comparing the code on the left to what's on the right, it seems like the actual functions in MIPS, instead of taking an item and then choosing a location for it, it looks like you choose the destination first, which is why v0 is listed before register a0 and a1. Am I correct in assuming that?
There is some kind of notation that MIPS uses where the result is always on the left and the parameters are always on the right.
Okay. Yeah, it's just reversed from general syntax, I guess, from languages. So it definitely seems to have some sort of learning curve because of that. Because generally we think progressively, like take this item and then put it somewhere. We don't really think about where it goes before factoring in the item itself.
Yeah. No, it's very complicated, I think. I think that the only way to understand more the assembly code is to read that at least once per week. Someone from the chat say to you that you have a sex voice.
I don't know. Hello, 13th Vessel.
Yeah, exactly him. Okay, any questions?
Nope.
So far, I think that was the only one I...
Okay. Okay. Actually, I cannot hear you quite well. I think that you need to raise your volume.
Is that a little better?
Yeah.
Okay. So I believe JAL stands for jump and link, and specifically what that does is it stores the return address in RA. So you could just use JSUM, which would jump to sum, and it would also run the command, but the problem would be there that you wouldn't store the return address, so your JR command at the end of sum wouldn't get updated. So that's
Yeah.
specifically what JAL does, in case anyone didn't quite follow that in your first explanation.
Makes sense. Thank you. Actually, we are going to talk about the return address, etc., on the next slide. And I want to explain also because on the second last line I'm using nope, which basically doesn't do nothing. Okay, next slide. So the code on the left and the code on the right are virtually the same. They do exactly the same thing. This is really tricky because it's how MIPS works, because it before to do the jump, it's like I would read that because it's faster. When a jump is called, the CPU fetch the next instruction and then set the program counter to the calling function. Finally, it just perform RA, which is the return address, that is equal to the current program counter plus 4, which is the amount of bytes per operation code, to set where to return when calling JRRA, because JRRA, as we see on the slide before, return to the calling function. I don't know if you guys can explain this better.
So basically, from what I gather, the JAL function automatically executes whatever comes immediately after it. So the unoptimized code, you would have to set a nup function to cancel out that execution. But to better optimize the code, you would instead put something else after the JAL that's actually useful. It would just reduce the code length by a single line, and after a while that piles up. You would end up saving a lot of space.
Exactly, because the weird thing about MIPS is that when you execute JAL, it will not actually do the jump straight away, but it will wait the next line of code, which is really tricky to read when you read some disassembled code, but it works like that. It's some kind of optimization that they have done. And yeah, that's it. Okay, that's everything for PlayStation 2 and MIPS. I just say the bare minimum amount of information that you need to at least do something. Usually what I do is, for example, there are many kind of operation codes like LI, GAL, add, JR, and every time that I don't know how that operation code works, I just search that on Google. So really, I just search JRL space MIPS, and on the first page of Google, I will have everything that I need. Okay.
It's also important to note that you can find MIPS documentation for the PC or PS2 explicitly. It does exist online. So,
okay.
And that's important to know because the PS2 has functions that regular standard MIPS does not.
Okay. Because the emotion engine from PS2 is some kind of variance of the standard MIPS, I think. If you can find that documentation, I can link that to the chat, or if you can link that on the chat directly.
I do have it somewhere. It will take a.
Okay, whenever you have time. And what else? ROM hacking, oops, I just jumped a slide. So RAM hacking, when we want to perform RAM hacking, we want to define the objective. So for example, the objective of this tutorial will be to modify the health bar of boss and enemies. For that, we use Cheat Engine, which is one of the memory analysis tool. That's my favorite one. And we want to search the value first by trial and error. PCIe2 will map the PlayStation 2 memory in this range of address. So once we know that we should search only for those kind of range of addresses, we will reduce from Cheat Engine the list of results. So I want to do that right now. So I will show how does it work. So I have my Cheat Engine here, I have my PS2 emulator, I will execute Kingdom Hearts 2 Final Mix. I have a save state because I want to save time. Okay, so I want to check the health bar of this bad guy. So I want to attach Cheat Engine to the PlayStation 2 debugger. I need to disable the audio of the game. And so once we start the battle, we want to pause the game for a moment, and we want to start to search the value, because we know that at that point the enemy will have some kind of HP bar already set. But we don't know what the value is, so we are going to set a no initial value. First scan. Oh, before that, actually, I want to set as the range 2, 1, 2, 3, 1, 2, 3, 4, and that's it. This is the address range of the PlayStation 2 main memory. So let's execute the first scan again. So now the results found are way less than before. And we start to remove some health from the enemy. So we can say now that the value since before has been decreased, but we don't know yet how much. And we do next scan. We can see that there are a lot of value changing here, but we know that we are not removing the health anymore because the game is imposed, so we can say unchanged value. With that we can restrict a lot the results found. So let's continue to play. Let's kick the guy, decrease value again, and those are all the values found. We can go again and change value, and I want to do a thing to make things faster. I want to reload the state as before. I want to restart the battle from scratch. Now I'm going to choose compare to the first scan, and compared to the first scan the value is unchanged. We still actually have a lot of results here. So for example, we want the game to execute some random code, but actually we are not hitting the enemy, so we can continue to perform the scan because we know that the value is still unchanged. So from all the values that we have here, the values that makes more sense are those three. So I want to reload again the states. I want to execute the battle again. I want to start to remove some health from the enemy. we can see that the value that is decreasing every time that we hit the enemy is the first one. So I guess that the first one is actually the value, the health of the boss. So just for testing, we can set that to 1. And now with a single attack, the enemy will just die. Yeah, it does have 1 HP. Ah, I'm dead, but anyway, I think that everyone's seen that now the enemy has only 1 HP, right?
Yeah.
So I will just reload the states and change the value in real time. So from 3168 to 1. When you hit that. So I want to store this value somewhere. 3168, so we'll just open a notepad instance and store the value somewhere. So we want to say enemy health 3168. Okay, I want to return to the slide because we have seen how to perform RAM hacking for now. So let me scroll again. So now we are interested about the ROM hacking. So how the game save that specific value in the memory, where the value is taken from, how we go to the source to, for example, get a table of all the health from all the enemies, and potentially we can even discover more statistics than the health. So with that we are going to use EDA, or free or the pro version should be the same. We are going to use the PS2 debugger. So EDA has some kind of naming convention. So every variable that starts with the word is a global variable. So that offset, which is now 000, contains a specific pointer or data that never change its position. So we know that every time that we start the game, that value will be always in that address. Sub is a subroutine, so, or simply a function, for example, sum, the function we defined before. Lock is just a location and is used for condition branching, so for example for loops, if then else, while, and things like that. So let's see how we can detect this value. So from cheat engine I know that this is the address where the HP are stored. How PCX2 works is that it maps the PS2 memory adding a 2 on the end. So if we just remove the 2 at the end, we are going to have the real PlayStation 2 address. So we want to open the emulator debugger, and we want to set a breakpoint. A breakpoint is basically that when a certain condition is reached, the execution will stop to that point that is triggering the condition that you decided to set. So for example, in our case, I want to go to the breakpoints tab, I want to add a new breakpoint, and what I want to say is that at that specific address, with 4 bytes changed, something is going to happen in the memory. For example, we want to know what function, what portion of code writes the HP amount of that enemy. So I want to set write. I'm going to push OK. I'm going to reload the state before the battle. At a certain point, the emulator will stop to that specific portion of code, which is MIPS, basically. So, for example, you can recognize the LI. But what is writing on that portion of address is this SW0T7. So if we have currently the value for T2 here. If we if you want to execute that specific line of code, we just need to press step into, and you can see the value will be changed to 0. So this is not actually the value that we want to. This is not the function is writing the information that we need. So I'm going to execute the emulator again and skip this function. So I'm going to click run. Now I'm in a different portion of memory. So when I click step into, I'm going to see that now I have the 3168 value. The operation code is SW, which is store word. A word is a 4-bit value. And we are storing we are storing T7 to the address of T5. If we can see the list here of registers, we can see we have T7, which is a certain CC0. If we open calculator, so for example we do calculator here, and we specify that CC0 value, we can see that actually that's 3168 in hexadecimal. And since SW is storing T7 inside T5, if we see T5 which value it is, so for example we do right click, change lower 64 bit, we can see this weird value here, which is exactly the address that we found on cheat engine. So we know that with that operation code we are writing to that portion of memory that specific value. I don't know if my explanation was clear at all.
I definitely understood it.
Yeah, I followed it as well.
Yeah.
Okay.
I mean, it's pretty straightforward.
Okay, nice. So, since it's straightforward, we are going to jump to the hard part. We want to disassemble the main executable of the game. So, right now I have my game mounted as a CD-ROM, and we know for a fact that PlayStation 2 games stores executables in this format. So I want to copy this item on the desktop and I want to drag it on EDA Pro. It will detect that is an executable done in MIPS assembly. I will click OK, and I will just
also
wait.
Make sure it's decompiled as little endian, because that's the endianness of MIPS.
True, good point, because PlayStation 2 uses little endian.
Yes.
So
and
now,
IDA has a setting to swap it to big endian, which is generally not.
Yeah, because as far as you know, once EDA completes the analysis, you cannot just swap the endian because it's going to recalculate everything anyway, so it's faster to start from scratch. So what we want to do here is, in theory we should wait the analysis to be finished, because it's still analyzing the situation. But in the meantime, we can start to jump to that portion of code that stores the HP value. So the address, the executable address that is storing that value is 180F48. So I want to go to EDA Pro to that specific address. So A0F48. And if I'm going to highlight that portion of code, is actually the same that the emulation debugger is telling to us. So we can say, for example, we can add a comment here saying store HP value, or even better, store current HP value. Now, where this T7 came from? Because I guess that comes from a game file or from the executable, so we want to track that information down and see where it comes from. And someone from the chat says, "Does then devs remove all the symbols from the executable?" Yeah, that's a big problem. In fact, we are hoping to have one day a debugging version of Kingdom Hearts 2, because at that point we are going to have all the symbols and it will be extremely easy to understand each function exactly what it does. But it's more fun in this way, so it's fine. So if we want to track down this T7, we have this is storing T7 from somewhere. This is doing a certain MFLO, which is some kind of floating point operation, but we don't care about it. And here we are dividing T7 with T3. So I wonder what it does. So we just add a comment doing T7 equal to T7 divided by T3. Yes, symbols means function names anyway, based on who is asking that from the chat. Here we have this weird thing here, which we are adding this 63 to T7. We have no idea what that 63 does mean. If I do a right click, I can see that there is a decimal value, which is 99, that makes slightly more sense than 63. 99 is more a decimal value, so it's like it's near 100, so we can imagine what's going on there. So we can do, for example, T7 equal to T7 plus 99. This is not using T7, so we can skip that line. We are doing here, we are multiplying T7 with T6, so we do T7 equal to T7 multiplied by T6. And I wonder what this T6 is. T6 is a value that has been taken from this T4. So here we are saying assign something to T6. We don't know yet what this does. T7 is loaded from here, so we can say assign some obscure value to T7. So we have a V0 here. V0, as we said before, is a returning value from somewhere. So I imagine that above there is some kind of function that is called that is going to assign V0 to something. In fact, I have here a function calling this way, another function calling that way. So I want to see what the game, what kind of function is going to call this on that one. So if I want to discover that, I will set another breakpoint to the beginning of this function. So I'm going to copy the address of this function, which is 1A0. I'm going to add a new breakpoint. In this case, I don't want to have a breakpoint when a certain memory portion of memory is read or written. I want to break when that specific address is executed as code. So I will pass that address there. And that's it really. I will disable this breakpoint here because I don't care. I will execute the game. I want to reload the states, skip the cutscene, and now the debugger is breaking at the beginning of the function, so we can recognize those operations code at the beginning. So we want to check if it's going to land here or there. So we are going to do step into until we are going to reach that specific value, that specific JAL. So the JAL has been done to 1C0 C80. So this is the function will be called. So we can say this process something that assign the result to bit 0. If we enter into the function, we can see that there are some kind of basic information, so I guess that this function is really easy to read. What it does is to 80 is our input value, because for example, if I want to open Notepad, I want to say, if I can copy this function, I want to say function something which I accept as a parameter 80. And all we know from now is that it's doing something. We don't know yet what. Can you guys follow me? Is that a no?
I'm sorry, I was so entranced I didn't even hear the question.
Okay. No, I'm asking if everyone is following me, or if I'm not explaining myself correctly.
I'm definitely following you, like, as you go.
Yeah, I'm following you as well.
Okay.
Yeah, I'm too.
Okay. So we reach this function with this parameter. We have no idea what that parameter does. We can see from the emulator that A0, which is here, is 63 here. We don't know 63 what it does. So we are going to say, we're going to take note that is called with 63 as parameter. 63 again is a weird value, it's an hexadecimal value, so if we convert 60 to decimal is 99. So I wonder what 99 is. For now we are going to store this kind of information here. So from the code, if we step into that function with the debugger, we can see that we are multiplying A0 with T7. What T7 is 1D50000, and we have no idea why we are performing this kind of operation. So we want to move forward. We are multiplying T7 with A0 and storing the result to A0.
T7 is C. You looked at T6 when you grabbed the value.
Excuse me?
T7 has a value of C, not 1D. That's you looked at T6. T6 has 1D5000.
Correct.
Okay, I have no idea why.
You're multiplying by T7 though.
Look at your register list. You looked at T6 instead of T7.
Yeah, true. So actually we are doing thanks for correcting me.
Yeah, so it's multiplying by 12, not some really big value.
Yeah. So we are doing 99 multiplied by 12. And we are storing this offset to V0. We are adding our 99 multiplied by 12 to be 0. So I wonder what this information does contain. I want to search it. I will go to cheat engine once again. I want to go to the memory viewer. I want to go to that specific address. We are going to append 2 because again we are using the emulator. And okay, we have a certain 0815D101. This is a pointer. This is usually how the game stores pointers. So for example, we are going to add a new address. I want to say we are going to call that field with this one, converting to hexadecimal. No, wait a sec, I forgot to add the 2. So this looks like an offset, some kind of address. So I want to jump to this portion of memory. I want to see what's the content. Again, I will add 2, and I have this kind of table. And in this table we are adding 99 multiplied by 12, so I guess that that's an array with 12 as a byte size, and the 99 is an index of that array. So we can say, for example, that we have a structure where we have integer A, B, and C, and we are going to the index 99. Now, I know that for who has not much programming knowledge, this is really weird, but let me show why I jumped to that conclusion. So I wondered this table where it came from. I guess that came from a file. So I want to, I would like to copy the first line. I want to go to the game data. So I want to open the extracted game files. And from the game files, I can see a bunch of files, since we are doing something related to battles, because the HP is related to the battle, basically the battle system. I have a 00 battle here, so I wonder if that's the file. I'm going to open that file with any hexadecimal editor. I'm using Hex Workshop. I'm going to search those hex values that I just extract from the memory viewer. And guess what? I found something. So usually it's not that easy. I knew that this information was into 00 battle, but I usually search the files that potentially can contain that information. I'm going to perform the exact operation. I usually don't search more than 3 or 4 files. So I want to, copy a bunch of data from here. I'm going to put that into a new file, and as we guessed, we are performing this kind of operation. So we are performing an index. We are searching through an index to a structure that is 12 bytes long. Again, how we know that it's 12 bytes long? Because we are multiplying A0, which was our 99, with 0C, which is our 12. It's just written over here. So we want to perform the same operation with any calculator. We do 99 multiplied by 12, we are going to get this exact value. We copy this value here, we jump to that offset from the beginning of the file, and we have this information here, which we had no idea what it does. So if we align the information like this, we can see that actually we are in some kind of table, because we can detect a pattern. We have 14, 15, 17, 18, so there is something going on here. Where are we? Where we are is like, again, I'm going to go to that offset. We are actually here or here. I have no idea anymore. This data makes more sense. This start to be quite different from the data that we have above. So I guess we can delete that. But before to delete that, let's see the debugger what kind of value is going to return. So we are multiplying the value, we are adding that value here, and then we are returning. So we want to continue the execution with the debugger till we are going to exit from this function that we can name like load something. And at that point we are here in this li exactly here, but I wonder v0 what does it contain. So I want to take the value from v0, I want to put that again here and see what is going to land. And actually here b5 00 5600 33, I want to copy this, I want to search that here, and we know that we are exactly at that point. So the rest of the information we don't need that. Spoiler alert, that 99 is actually the level of the boss. And those are all the statistics per level. So internally, every enemy has a level, and based on the level, there are some kind of values that are multiplied by some other values. We want to continue the execution of the program. This we have 64, which we have no idea what it does, but as a decimal is converted to 100, which makes more sense than 64, so we are going to stick with this change. And are you still following me?
Yes.
Okay.
Yeah.
Sometimes I'm afraid that I'm talking a lot. That I'm only able to follow myself. So we are doing, so after this load something, we can say that it actually loads enemy statistics. And I have to do a weird thing here. So basically, just say please set up the compiler options in option compiler. So let's do it. So option compiler, we want to set Xeeynamo, which is the compiler that the PlayStation 2 SDK uses. And if I do right click, what is that? Right click, set type, we can say that A0, which is the function parameter, is actually an integer called level. And the return value is some kind of, I don't know, some kind of information. But actually, since we know that information is 12 bytes long, we can define a structure here. So we do new structure bar. This we can call, for example, enemy statistics, which will have 12 bytes long. So we can say one word, another word. So we had the size of that structure is actually 0C, which is that 12 value that we detected before. So from EDA we can say for certain that we are returning an enemy, I don't even remember how I call that, enemy statistics. So magically we know what that kind of function does, and we know that this is the very first value of the table, which is this. So we can say for certain that this dword is actually a pointer to enemy level table. This 12 is structure size. So now we know that load enemy just store on v0 the statistics table. So we know that this is not anymore assigned some obscure value to t7, but this is loading from v0, this is loading the first integer to t7, and t7 at a certain point will be stored as HP. So we can say on the structure that the first field, because we know the field 0 is actually the 0 field from v0, we can say for certain this is the HP. But again, we are multiplying that value with something, with a T6 that we have yet to know what it is. T6 comes from T4.
Do you mind if I interject really quick?
Yeah, sure.
So we can see that load statement right there, where we load T7 is LHU. So that's load half words. So should we update our struct, since it seems like it's in half word increments, not word increments?
Thank you. So that would be a word, sorry, a half. So we have another unknown field here. So yeah, good point. So that HP is a short. It's 2 bytes long. Good catch. And so we missed just this T6. So we can say on the command, we can say that T7 is actually HP T7 multiplied by T6. T6 comes from T4, but we don't know yet what T4 is. T4 is calculated, he is doing T4 plus 6. T4 is equal to S1 plus 4. But we still have no idea S1 what it is. S1 is assigned from A1, which is the second parameter. So we know that this parameter comes from a function that is calling this function here. Judging from the length of the function, we can say, for example, we can rename this function called sets enemy statistics. I'm curious, I wonder what A1 is. So I want to go again to Debugger. I want to check A1 or S1, they are the same thing, because we are saying here that S1 equal to A1. I want to get the value data. Actually, let's go here, let's copy that, let's go to cheat engine, go to that specific memory address, and we have all the information. We have no idea what they contain. So I just copy that. I will return to my 00 button that I load on the very beginning. I want to search again that X value, and I just found another thing. I have this weird F263D06. I have no idea what it does, but for now we are going to reduce that as an icon. We can see that we do S1 plus 4, so I guess that from here is not logging in 0, not 1, 2, 3, 4, so it's logging this value here, D606. If we continue the execution of this code, is doing actually T4 equal to S1 plus 04. So we are here right now. I want to check what T6 is going to extract from T4. So we want to move forward, we want to reach that LHU. And we can see that from T4, T6 now has exactly that value. D606 is the red value over here. So we actually know that we discovered some kind of logic where we say that 99 is the level. Then from the level is extracting, let's go here again, at the bottom is extracting the first value, which is B5. B5 in decimal is 181. So this HP from level. And then we have 6D6. 6D6 in decimal is 1750. We are multiplying, let me write that somewhere, 1750, this comes from A1 slash S from T4. So we do T6 multiplied by T7, we add 99, and then we divide it by T3. T3 is 100. So let's perform exactly this logic that is written here. So we do 181 multiplied by 1750 plus 99 divided by 100. And we have 3168, which is actually the value, the HP value that we say at the beginning. So we know that the amount of HP came from those two tables that are contained inside this file. One from here, this D606, and the other one from this kind of weird table. So for cutting the video short, because it's already 1 hour since we are going, I made my research previously, and I discovered that on 00 bottle, 00 bottle is actually a container of multiple files. We have we have some kind of tables. One is called LBPM, if we open LBPM, we can recognize the 14 that we see at the beginning, and from the end we can recognize that B5. So if we align again the data, we know that those information are exactly the same. And here I'm guessing, so if the file size is 4A4, so let's do here 4A4, and every information is 12 byte, which is in hexadecimal is C, we obtain 99. So my guessing is that this is the table which multiplies the statistics for every enemy based on their level, and the maximum level of an enemy that can get is 99. The other table, from the names we can see this NNMP, so I guess that that's the value, the table refers to the other information we found. We wanted to find D606. There you go, found. So now that I know what files store that value, we know that the HP is a multiplication between values from two files. We can now edit this value here and this value here to modify using ROM hacking the amount of HP of that enemy. And this is it really. So recap, we use cheat engine to find the information that we wanted to modify through ROM hacking. Once we found the information, we got the address of that information, and with the debugger we have seen what function is writing or reading to that location of memory. Using both the debugger and EDA, we are detecting how that value is really calculated and where that value comes from. Using the game data, we can understand where is the origin of that specific data, so we can modify it and we can create a library or a tool that modify that information to create, I don't know, an enemy editor that modify, for example, in our scenario, the HP. With more research we can find, I guess, attack, we can find defense, we can find all those crazy things that actually are already been found and documented on OpenKH documentation. And yeah, I finished. Silence.
So did you ever find out what the other values in the tables were?
Yes, actually yes. I think that they are located somewhere. Let me check. Bash. It's like let me see, cd the repository Xeeynamo codes git checkout master 00 battle. Oh, actually, I found that from that NMP, I have ANMP loaded here. If I can try to find some kind of alignment, if you recall correctly, D606 came from a certain value plus 4. So the beginning of the structure is actually F2. F2 is actually Roxas data statistics, so I found that based on the index, every index is assigned to some kind of specific enemy. I have in another branch, if I do git branch, I do git checkout feature 00 bottle, and I didn't write yet the documentation, I think, but I write that on the structure. If I go to OpenKH bottle ANMP, the first value is the ID, then I have the level. Oh, true, the level. I didn't notice that the 63 that we have here is actually the level of the enemy. So we have ID, level, the health. This is an array of health. I have no idea why the game processes that information like that. The physical weakness, fire weakness, some kind of bunch of elements. I even found that there is reflect weakness. I have no idea why the game doesn't need that information, but it's always set to 100. And yeah, that's it. And for the LBPM, we have some kind of HP multiplier, because it's multiplying as we have seen this health here with this HP multiplier based on the level. I have exactly the logic that I extract from the disassembly. This is the attack value. I didn't found yet what is the purpose of those. The idea will be, for example, to place some read or write breakpoints. Actually, the write is not needed because we already know where that information came from. We must need to place a read breakpoint and see how the game processes that specific value.
Right.
But yeah, that's it. So I will conclude before any other question. The last slide, saying thank you for arriving till the end, because I know that my accent is kind of terrible. I'm not good at explaining. I never do this kind of stuff usually. So thanks for listening to me. And the project, everything is called OpenKH, which is a project that centralizes all the technical knowledge of Kingdom Hearts series in one place, providing documentation, tools, code libraries, and the foundation for modding the commercial games. As more or less I say to the beginning of the video. You can find all... Oh, the fuck is that? You can find all the source code to this specific link. You can find all the documentation from the second link. And if you found this talk interesting, I'm referring to the guys that are following me from YouTube. We are waiting for your amazing contribution. Done. Can I escape now? Questions?
Thank you for the tutorial slash showing us the process you use. It was very helpful for me at least.
Yeah, it provided some nice insight. I've personally not really messed with the BCSX2 debugger too much, so seeing that process was pretty interesting.
I think that the stuff that I show, mostly the debugger, is not really hard to understand. I think that EDA is way more complex to use, but
it definitely is.
yeah, I think that the main point is that once that someone knows how to do something, I think that instead of keeping that knowledge for us, just worth to share it, because we can proceed to work together faster. So yeah. And I'm reading from the YouTube live chat that the people seems to be happy with my tutorial. So yeah, I want to close this here because I don't want to continue to blush in live. So thanks people from YouTube, and see you next time, I guess. Bye bye.